Okay, welcome students to video class number 18. In this session, we are going to study about type of transfer function and steady state error. In the last video, we have seen that the steady state error depends on, okay, the steady state error depends on two things. One is the input, the other one is the GSHS. Now, GSHS is actually called as the open loop transfer function of a closed loop system. Now, in the after that, we have just seen how this steady state error varies according to the inputs, and thereby we went on to define three different static error coefficients: positional, static error position coefficient, positional error coefficient, velocity error coefficient, and acceleration error coefficient Kp, Kv, and Ka. So based on that, we have defined the steady state error. That means Kp is corresponding to unit step input, Kv corresponds to unit ramp input, Ka corresponds to unit parabolic input. So in a sense, we have actually studied the relationship between, or the steady state error as seen in this equation, how it relates with this input side. Now the next in this video we're going to the second part, that is the steady state error also depends on the value of GSHS, and GSHS is what is called as the open loop transfer function of a closed loop path. Now let us see. I will just again explain what is this open loop closed loop transfer function, that is GSHS. So we know that GSHS is called as the open loop transfer function of a closed loop path. Okay, of a closed loop path. Right now, I will explain this. So this GSHS is actually equal to it can be generally represented as K into 1 plus STA into 1 plus STB, etc., divided by 1 plus ST1 into 1 plus ST2, etc., into S raised to n. Okay, so this is how an open loop, general open loop transfer function is defined. So if you can now you can, if you analyze this, you can have four different terms like K, which is called as a constant, or this is also called as a forward path gain. Forward path gain. Okay. Now, then you have a 1 by S raised to n term. You have a 1 plus ST8 term, and you have a 1 plus ST1 term, or 1 by 1 plus ST1 term, right? Now this is 1 plus STA, 1 plus STA, these are all the same terms. So these are the four different terms that you can see in this open loop transfer function: constant, then you have a 1 by S raised to n term, 1 plus STA terms, and 1 by 1 plus ST1. These are all important when we deal with the module 4, when we come to various graphical plots. Okay, we'll come to that later anyway. Now, this is it. So, when you analyze this, so you know that this is the denominator term, or this is actually, this g of s, h of s can also be called as it's a polynomial, right? P of s to q of s, and you know that when you equate P of s to 0, you will get zeros. When you equate Q of s to 0, you will get zeros. So poles, right? So from this, when you equate this to 0, you will get this as s is equal to minus 1 by Ta. If you get this, you will get this as 1 by Tb. Okay, so this will be, so these are the various roots of this: 1 by minus 1 by Ta, minus 1 by Tb, etc., as you equate every terms. So similarly, when you equate this to 0, that is PQ of s to 0, you will get this as minus 1 by T1, minus 1 by T2, and so on, right? So these are called as the poles, and these are called as the zeros. Okay, all these things you know. Now coming to this term, there is a term called as 1 by s raised to n. Now you know that if there is a term called as s, when you equate this to 0, this actually denotes s is equal to 0. Okay. Now, say for example, if you have s square, what's the meaning of this? This is actually 1 by s into s. So if you equate this to 0, you can see that there are two poles. These are all the poles. This refers to the fact that there are two poles residing at the same location, right? Residing at the origin, or we call as the multiple poles, right? So if n is equal to 1, you will say that there are only one pole. If n is equal to 2, you will say that poles at the origin will be 2. If n is equal to 3, you will say it is 3. So based on that, you can classify the system as type system. Type. So this is actually called as a type n system. Okay. So what do you mean by type 0 system? Type 0 system is a system where you have only one pole at the origin. If n is equal to 1, that's a type 1 system. Okay. Now if n is equal to 0, that is for example n is equal to 0, then this will be 1 by s raised to 0, which is equal to 1, right? So if there is no term called as s raised s term at the denominator, you can say that that is a type 0 system. So you can have type 0 system, type 0, type 1, type 1, type 2, and so on, right? Now we are going to study about this type, the type of the transfer function and the steady state error. So we are going to correlate, is there any relationship between steady state error and this type of the transfer function, just as we have seen in the previous video, the steady state error and the various input. Okay. Now, so now we are going to study about the or estimation of steady state error, steady state error for different types of transfer functions. Okay, so first of all, to start with, let us consider a type 1 system. Okay, now in the type 1 system, say consider a system, assume that this is a type 1 system. Now what's the meaning of type 1 system? Type 1 system is a system whose open loop transfer function, the general open loop transfer function, will be given by k into 1 plus sta into 1 plus stb, etc., divided by 1 s raised to. So we are going to study about, it's not type 1 system, it is type 0 system. So when what happens, what is type 0 system? Type 0 system is a system where n is equal to 0. So this is s raised to 0 into 1 plus st1 into 1 plus st2 and so on, right? This is a generalized transfer function. What is this s raised to 0? S raised to 0 is equal to s raised to 0 is equal to 1. Okay, so this is it. Now this is the transfer function that we are considering, or this is a type 0 system. Okay, now next is, now for this type 0 system you can have so what will be your steady state error? How will you define this steady state error? Now we know that Kp, in the last class we have studied Kp to be equal to, so if you have doubts you may refer that. Kp, how will you define this Kp? Kp is limit, Kp is actually limit s tends to 0 GFS HS, right? So this is Kp is equal to limit s tends to 0 GS HS, right? right? Now what is this GSHS? We know that limit s tends to 0, k into 1 plus STA into 1 plus STB, etc., divided by, okay, divided by s raised to 0, that is 1. 1 into, because this is a type 0 system, 1 plus ST1 into 1 plus ST2, okay, into etc. and so on. Now what happens when you put s is equal to 0 over here? Now you can put the limit, so that limit has nothing to do with this k because it's a constant. All other terms becomes unity, right? This becomes 0, this becomes 0, meaning this is 1, this is 1, this is 1, and all these things are 1. So that this kp is equal to, we found out to be, is equal to the forward path gain. Okay, this is the forward path gain. So k is equal to, kp is equal to k, or we can say that the steady state error will be equal to, so the steady state error with the error will be equal to 1 by 1 plus kp, or this is equal to 1 by 1 plus the forward path gain. This is for the case when the input is what? Input is a unit step. Okay, so again repeat this. This is a type 0 system with what? With unit step input. With unit step input. You are giving a unit step input to a type 0 system and you're analyzing that. So when you find out the output, the steady state error, we know that this is 1 by 1 plus kp, but from this we understood that when you apply this kp to this general transfer function of a type 0 system, we found out that it to be the forward path gain. So it is as if it is equal to 1 by 1 plus k. This is the case for a unit step input. Now, coming to the second part, which is a type, again we are considering the type 0 system with a unit ramp input. That is, you're considering a type 0 system with r of t. Okay, now what is going to be its effect? We know that for r of t, we have defined something called as kv, right? Kv is, that is a positional, velocity error coefficient is equal to limit s tends to 0 s into GSHS, right? So hope you have an idea. So we have studied that. So look at this. Look at this. So this is how we defined kv, right? Kv is 1 by limit s tends to 0 s into kv is equal to limit s tends to 0 s into GSHS. This is actually 1 by kv. So kv is this thing. Now I'm rewriting that again. Limit s tends to 0 s into GSHS. Okay. So what happens? S to 0 into s into 1 plus STA into 1 plus STB into etc. divided by 1 plus ST1 into 1 plus ST2 etc. Okay. Now what is this s raised to n? S raised to n is s raised to 0, meaning it is equal to 1. Right. This is a type 0 system. Now when you apply s tends to 0, the whole thing becomes equal to 0, right? Okay, so kv becomes equal to 0. Now we have seen that for a unit ramp input, your ESS, the steady state error, is actually found out to be what? Found out to be 1 by kV. ESS is 1 by kV, or you can say that this is equal to 1 by 0, or this is infinity. Okay. So what is this? Look at this. For a type 0 system, The steady state error depends on the forward path gain. It is an inverse, having an inverse relationship. ESS will be 1 by 1 plus k, and if forward path gain can be minimized, then you can say that the steady state error will also be minimized. But what about the second case? When you give a ramp input to a type 0 system, the steady state error is going to be infinity. So, for a type 0 system, the only now as from this discussion, yes, unit step input is favorable because there is, even though there is error, we can minimize by the design procedure. Okay, forward path gain is a gain which the designer designs, right? So designer has the freedom to minimize this, so to select this k value so that he or she can make sure that this ESS can be reduced. While in a type 0 system, we have seen that the steady state error with the type 0 system with the unit ramp as the input, we have seen that the steady state error is the inverse of this one by kV, which we found out to be infinite. That means if it is the ramp input that you give for any type 0 system, the steady state is going to be infinity. So that means this ramp input is not suitable for a type 0 system. Okay. Now there is just a correction, a simple correction in the second one. Type 0 system with a unit ramp, there is a k also here, so you may just correct s into k into 1 plus st. That has got no relevance here as because the value is infinity. Anyway, you should add this k. Okay, this is k. This k has to be written here as well. Okay. Now coming to the third case where you are considering again a type 0 system, with parabolic input. Okay, now we know that. So that means you are considering a type 0 system. You are giving an input of parabolic input. Okay, now what is the error coefficient associated with this associated with the acceleration? So that is the parabolic input, that is called as the acceleration error coefficient, and it is represented as Ka, and Ka is given by limit s tends to 0 s square gs hs. Okay, that we have studied. So rewriting that, Ka or acceleration error coefficient is given by limit s tends to 0 s into s square into gs hs, right? Okay, now when you can just find out for a type 0 system, s tends to 0 into s square into, what about this, k into 1 plus sta into 1 plus stb, and it goes on like that, divided by s raised to n, because type 0 system s raised to 0 becomes 1 plus st1 into 1 plus st2 and so on. So when you put s is equal to 0, this automatically becomes 0. So that means k is equal to 0. But from our previous discussion, we have found out the steady state error in static error acceleration error coefficient as 1 by Ka. Now when you evaluate this ASS here, this will be 1 by Ka, or this is equal to 1 by 0, which is also equal to infinity. Okay, so from this we have found out that, so we are just going to conclude this. For a type 0 system, the only favorable input is the u of t. U of t is the favorable input. When it comes to r of t, what happens? The steady state error is infinity. When it comes with the parabolic input as well, the steady state error is found to be infinity. So from this discussion, we can see that for a type 0 system, the permissible input is what? Input is a unit step. Why? For all the other inputs, this system gives a steady state error of infinity, while In a type 0 system, even if it provides a steady state error of 1 by 1 plus k, we have seen that that can be minimized by suitably selecting the forward path gain. Okay, so that's it. That is ramp and parabolic are not acceptable for a type 0 system. Okay, type 0 system. So a question can be asked that prove that for a type 0 system, ramp and parabolic inputs are not acceptable. So you can just have this derivation. This is quite simple. Now let's move on to the three cases of a type 1 system. So far we have seen three cases of a type 0 system with the unit step input, with unit ramp, and unit parabola. Now let's move on to type 1 system. And in type 1 system also, so okay, let me give a heading here. So you may just do like this. This is type 0 system. So in this type 0 system, there are three cases. Similarly, we are going to consider a type 1 system. Now, let me first of all introduce the GSHS. What will be your GSHS? GSHS will be, okay, K into 1 plus STA into 1 plus STB into, right, etc. divided by S raised to 1. So since it's a type n system, your n is equal to 1. So this is S raised to 1 into 1 plus ST1 into 1 plus ST2, etc. Right? Now if this is a type 1 system, now this is the case 1, that is a type 1 system is subjected to a unit step input. Okay, so type 1 system with unit step input. That means you have a system which is a type 1 system. What's the meaning of type 1 system? In a type 1 system, when you draw the pole 0 plot, you can see a single pole residing at the origin. Okay, in a type 0 system, there is no pole. A type 1 system, you can have a single pole at the origin. So such a type of system, say you are giving an u of t. Now when you give a u of t to this, we know that we have already defined the u of t, the steady state error in terms of the static error coefficient, positional coefficient, right? So the steady state error is given by 1 by 1 plus kp. Now what is kp? Kp we have defined to be limit s tends to 0 s into, sorry, it is not s, it is into GSHS, right? You need to be very careful. Just if you have any doubts, look at the previous video. So this is it, limit s tends to 0. Now when you apply this limit s tends to 0, k into k into 1 plus STA into 1 plus STB into, okay, divided by, what is this, s raised to 1, s raised to 1 into 1 plus ST, 1 into 1 plus ST2. Okay, so this is type 1 system. So that what is your Kp now? Now when you apply limit s tends to 0, what happens? 1 by 0, right? This is 1 by 0. So all other stuffs becomes 1. So this becomes 1 by 0. That means this becomes infinity, right? Now what is a steady state error? Now what is a steady state error? ESS is given by 1 by 1 plus Kp, or this becomes 1 by 1 plus infinity. What is 1 by infinity? 1 by infinity is 0. So what do you infer from this? For a type 1 system, if you give u of t as the input, that is the step input, the steady state error is 0, meaning this is an acceptable input. Now coming to the second case, where you consider a type 1 system, with ramp input. Okay. Now in the ramp input, we have seen the steady state error to be equal to 1 by kV, right? Refer the previous video. Now what is this kV? kV is limit s tends to 0 s into GSHS, right? Okay. Now, what you are considering is, you are considering a type 1 system with R of t as the input. Now, what is the meaning of a type 1 system? You must always keep this in mind. There is a single pole residing at the origin. So, for such a type of system, your KV is found out to be this, and if you, the inverse of KV is the steady state error, which we have dealt earlier. Now, to find out this, using this general transfer function, you will get this as S into 1 plus K into 1 plus STA into 1 plus STB divided by etc. divided by S raised to, that is S raised to 1, right? So this is S raised to 1 into 1 plus ST1 ST1 into 1 plus ST2 and so on, right? Now when you apply, so you need to cancel first of all before applying the limit. So there is no S term, that means there is only some S terms here. This becomes 0, this becomes 0. So altogether it has 1, 1, 1, 1. So this becomes equal to K, right? Now what is a steady state error? So steady state error is nothing but it is the inverse of the forward path gain. This is the forward path gain. So this is 1 by K. Now if the designer can suitably select this K, he can reduce the steady state error. So this is also an acceptable input provided some changes are to be done for the forward path gain. Now coming to the third type, the third case where we consider a type 1 system with a parabolic input. Now what happens with the parabolic input? That means you are considering a T1 with the P of t, with the parabolic input. What's going to be the effect? So do remember, you have only one pole at the origin. That's why it is called as a type 1 system. Now we know that the steady state error, we have seen in the previous video, the steady state error for parabolic input is given by 1 by Ka, where Ka is defined as limit s tends to 0, s square into GSHS, right? S square into GSHS, right? Now limit s tends to 0, s square into, what is this? K into 1 plus STA into 1 plus STB, etc. divided by s raised to 1 into 1 plus ST1 into 1 plus ST2, etc. Right? Now this S and S get cancelled. You have one S. Now whatever there is the value of S over here, you just apply S is equal to 0. So this becomes 0. So Ka becomes equal to 0. Now what is your steady state error? Steady state error is 1 by 0, which is equal to infinity. So from this discussion, we have seen that you have 3 inputs. Among this, for type 1 system, for a unit step input, so the steady state is 0. So this is acceptable. This is acceptable. Okay, this is acceptable, and this is also acceptable because you have, even though you have a steady state error that can be controlled, while you can see that for any type 1 system which is subjected, if it is a parabolic input, then the steady state is going to be infinity. That means this input is not acceptable for a type 1 system. Okay, now similarly we are going to study about the case with the type 2 system. Now we are going to consider a type 3 system, type 2 system. In a type 2 system subjected to various inputs. So what is the meaning of type 2 system? N is equal to 2, or your generalized transfer function will be GSHS is equal to K into 1 plus STA into 1 plus STB divided by etc. divided by S raised to 2, right? S square into 1 plus ST1 into 1 plus ST2, etc. Okay. Now in this type 2, we are going to consider the case 1 where the type 2 system with what? With unit step input. Okay, with a unit step input. Now we have already seen that the steady state error for a unit step input in terms of positional error coefficient is given by 1 plus k P, right? 1 plus Kp, where Kp is given as Kp is equal to limit s tends to 0 Gs Hs. Okay, now you rewrite this term again over here, so you will get this limit s tends to 0 as K into 1 plus St A into 1 plus St B, etc., divided by s square into 1 plus St1 into 1 plus St2, meaning that there is no term to cancel of this. When you apply s tends to 0, this becomes 1 by 0, or this is equal to infinity. We know that the steady state error is 1 by 1 plus infinity, which is actually equal to 0, right? So for a type 2 system, this unit step is acceptable because of the fact that the steady state error is 0. Now coming to the second state, where you consider a type 2 system with the unit ramps input, okay. Now in the unit ramp, we have seen that the steady state error is found out to be 1 by kV, or the velocity error coefficient, where kV is defined as limit s tends to 0 s into Gs Hs, right? So substituting that equation again here, limit s tends to 0 s into K into 1 plus Sta into 1 plus Stb, right, etc., divided by s into 1 plus St1 into 1 plus St2, right, etc. Now this is s square, right? This is 1 by s square, and this s and s cancel. Again you have an s, so this becomes 1 by 0, and that is infinity. Now what is the steady state error? Steady state error is, what is the steady state error? Steady state error is 1 by kV, or 1 by infinity, which is also equal to 0, meaning this unit ramp is also acceptable. Now considering the type 2 system with unit parabolic input, okay, with unit parabolic input, we have seen the steady state error to be equal to 1 by Ka, which is the acceleration error coefficient. K is given by limit s tends to 0 s square into Gs Hs, right? So this is actually equal to s tends to 0 into s square into Gs, K into 1 plus Sta into 1 plus Stb, etc., divided by s square into, why s square? Because it's a type 2 system, s square into 1 plus St1 into 1 plus St2, etc., right? Now this s square and s square get cancelled, so when you apply limit, this becomes unity, this becomes unity, this one unity, so this is equal to K, which is equal to the forward path gain, or the steady state error will be equal to 1 by K, or this is again a steady state error, but a finite steady state error, which can be minimized by suitably selecting K. So this is also acceptable. Now from this discussion, we have seen that for a type 2 system, the unit step is acceptable. Okay, this is acceptable. Now this one is acceptable, this one is also acceptable, right? Okay, now let me say two. We have studied in the static error coefficient. With respect to static error coefficients, we have also related the static error coefficient with the type 0, type 1 and type 2 system. Okay, now let me just have a tabular column of that. Say you have a type 0 system, type 1 system, and type 2 system, right? Type 2 system. Okay, the input is u of t, r of t, that is a unit ramp, and p of t, unit parabolic. Now what you have studied is, in a type 0 system, the types in a type 0 system, what we studied is this is the error, the steady state error for the type 0 system, which is subjected to unit step input. This is acceptable, this is not acceptable, not acceptable. For a type 1 system, u of t is acceptable, r of t is acceptable with the some restrictions of, okay, this is not acceptable. While in a type 2 system, all the inputs are acceptable. Okay, so this is very important. This can be asked in your, I mean, either to prove this, or problems can also be asked in terms of this. Okay, so you must know what are the steady state error, why these are all acceptable. So in a type 0 system, we have found out this to be 1 by 1 plus k. If you can regulate your k, you can use this system. But in all these cases, you have found out the steady state error to be infinity. This is also for in a type 1 system. We have seen that in a type 1 system, this is again the steady state error is 0. This becomes 1 by k. The steady state error, this is infinity. So that's why we are not accepting this. Now in this case, we have just seen that this is equal to this is 0, this one is also 0, this one is also 1 by k, which is also can be restricted. So thereby all the three inputs are acceptable. Okay, hope you understood this. Okay, now we are going to consider a type 1 system with a unit ramp input, right? Unit ramp input. Now, when you write this error equation, so we have just seen the error equation is E of s is z0. Okay, you know how you got this. This is c0 plus c1s into. So this will be, now look at this. This is a general expression. Now, we have also seen that denominator, this is the polynomial gs is, or when you take the transfer function will be ds by ds plus k into n of s. Now what is the denominator of a g of s or gs into hs? So the denominator is actually, we have seen that this is your denominator, right? S raised to n. Now in the case of a type 0 system, there is no value for this. So when it comes to to a type 1 system, you have at least a term called as s. So that means the denominator, when you go for this type of evaluation, you are not going to find out c0 there, right? So the minimum factor will be s raised to 1, because you have a term in the denominator, you have a term called as s. So that comes in the numerator when you take e of s to r of s. So minimum you should have a yes. You cannot have a constant term. So that your steady state error or e of s, upon calculation, you will get this as c1s into c1s plus c2s square plus c3s cube and so on into r of s. Now here you are considering a unit ramp input. Okay, I'm just doing it for just a relation. That is, in the first case, we have considered a type 0 system with a unit step input. Now you are considering a type 1 system with a unit ramp input. So when you consider unit ramp, this will be 1 by s square, right? Now this e of s. Now let us see what is ESS. ESS is actually limit s tends to 0, s into e of s, meaning this will be limit s tends to 0, s into e of s means this s into c1s plus c2s square plus c3 s cube, etc., divided by 1 by s square, or this and s cancelled. Now this you can write like this, right? Yes, c1 by s, c1, this that will be 1 by s. Now when you multiply into this, you will get limit s tends to 0, z1 plus c2s plus c3, yes, right? And when you apply limit, you will get this as c1, right? So your steady state error becomes equal to c. Now we know that for a steady state error, for a type 1 system with a ramp input is given as ESS is 1 by Kp, right? So this is 1 by Kp or C1. So from this you can have that. So the steady state error for a ramp input of a type 1 system is 1 by Kp. ESS from the dynamic, in terms of dynamic, you call this as C1. So you can come to a conclusion that C1 is nothing but 1 by Kp. So this is a relationship. Now we are going to find out, consider type 2 system with unit parabolic input. Okay, when you consider your parabolic input, your RFS becomes, okay, 1 by S cube. Now what will be your E of S? Now, as I explained earlier, the minimum, so E of S, in the E of S, the minimum power, the lowest power must be S square, must start from S square, because it's a product of a division. So the minimum must be, so this will be E1 is equal to C2 into S square plus C3 into S cube plus C4 into S raised to 4, etc., the whole into 1 by S cube, right? Now what is ESS steady state error? That will be limit S tends to 0 S into E of S, right? So this becomes S into, limit S tends to 0, S into C2 S square plus C3 S cube plus C4 S raised to 4, etc., divided by 1 by S cube. This, so it becomes S square, this S and S cancels, right? So what you will get this as, so now similar to this, when you do the operation, you will get this as C2 into 1 by S square. So the C2, this becomes C2, then C3 S plus C4 S square, etc., as limit S tends to 0, right? Limit S tends to 0. So you will get this as C2. Now we know that the steady state error for a ramp, for a parabolic input of a type 2 system, we have proved to be ESS to be 1 by Ka, or you can come to another conclusion that C2, that is the dynamic coefficient, is equal to 1 by Ka. Okay, so if you're asked to find out the relationship between dynamic input and dynamic error coefficient, static error coefficient, this is the way it should be done, because in a static error coefficient we have only 3 static error coefficient, that is a positional, velocity and acceleration, and that is related to unit input, unit step, unit ramp and unit parabola. And that's the problem with the static error coefficient. But while dynamic error coefficient, because dynamic error coefficient can be called as a, can be considered as a generalized error coefficient, because you can find out the error at any time, and not only that, you can find out the error for any type of input. And one more thing which is to be added, so this so look at this, as we have defined this, this is this, so you are getting a series when you take the denominator, when you do this division, long division, as you do, this series is what is called as the error series. You may note down that, I just forgot to specify that. So this is called as the error series. Okay, hope you understood this. Now let's move on to dynamic error coefficient. So far we studied about the static error coefficient. Now the question is that enough? The answer is no. The reason is, so there must be some limitation for this steady state error. Number one is the steady state error, as we have studied, the static error coefficient. The static error coefficient is defined only for 3 inputs, that is the step, then ramp and parabolic, right? And not only that, the steady state error cannot be at any time, cannot be evaluated using the steady state error, static error coefficient. Okay, now the static itself refers to that it approaches the steady state, and the error cannot be evaluated at a particular instant of time using the knowledge of the static error coefficient. So in order to generalize this, so this can be applied to any inputs. So if in this in the static error coefficient, we only consider these three inputs. Now there can be lot of inputs other than these inputs. So in that case, how will you evaluate this steady state error or this error? You need to have an idea about the steady state error at any instant of time for any input. So we need to have a general error coefficient, which is called as a dynamic error coefficient. So we'll start with the thing that we have studied in the previous video. That is, we have derived an equation for E of S, right? That is the error, the frequency domain of an error signal. So it is E of S by R of S given by 1 by 1 plus GS HS. I am rewriting that. So this is E of S by R of S is equal to 1 by 1 plus GS HS. Okay. So this is actually the equation for the error error. Now consider the system to be a unity feedback system. Now what is a specialty of a unit feedback system? In a unit feedback system, your h of s becomes equal to 1, so that this equation becomes 1 by 1 plus gs, right? Okay, right. Now let's see this E of s and R of s, right? Now suppose your g of s, imagine that your g of s can be written as some n of s by d of s, meaning numerator polynomial and denominator polynomial, equating that, okay, say some constant k. Equating that in this equation, we'll get this as 1 by 1 plus k into n of s by d of s, right? Or when you take the LCM, you will get this as d of s divided by d of s plus k into n of s, right? No problem, right? So this is it. So you can carry out actual division by keeping the numerator and denominator polynomials in the ascending power of s. So what it does is, we just want to know this E of s. That is, what you are doing is you are dividing E of s to R of s in this way, right? In such a way that keeping the in the ascending power of s. So what I mean to say is, if this is s raised to 0, then the next term will be s raised to 1, next term will be s square, and so on. This is the ascending power. So you can perform division accordingly. Okay, in the signals and systems, we have studied about long division method. Hope you might have you might be remembering that, how we can divide in the ascending order as well as in the descending order. So you can divide that, and you will be able to get this E of s to be E of s is equal E of s by R of s will be equal to what? Will be equal to, so the first term, let us call that as a C0, let it be a constant, right? We do not know, so C0 plus next term will be C1s, right? We do not know, so we am calling this as C0, C1, C2 square, right? Something into s. So this will be C1s raised to 1 plus C2 s square plus C3 s cube and so on, right? Okay. Now that is E of s, right? So this can be written as Z0 plus Z1s plus C2s square plus C cube C3s cube, etc. The whole into R of s is actually equal to your E of s, right? Right. Now what if I take this, this is actually C0 of R of s, This is C0 into R of S plus C1 into S into R of S plus C2 into S square into R of S plus C cube C3 into S cube into R of S, etc. Right. Now you can find out the inverse of this. This is actually E of S. Now what if you find out the inverse? So you'll be getting E of t, right? This is what I told you. So when you take the error signal, what is actually R of S? R of S is actually the Laplace transform of R of t. It is not RAM, it is a general input. So you are considering a general input with R of t and C of t. Okay. Or to be specific, you are considering a unity feedback system like this, minus this is your R of t, this is your C of t. So when you found out this error, you can find out this E of S by R of S to be 1 by 1 plus gs. Okay, all these things we have proved earlier. Now when you take the inverse of this, we know that this is the R of S. Do remember, this R has nothing to do with the RAM. This is general input. So R of t. So when you take the inverse of this C0 will be C0 into R of t, right? Because the Laplace transform of R of t is R of S. That means the inverse of R of S has to be R of t. Plus S into R of S. So S into R of S is related to what? You have studied something like this. So if you have f of t whose Laplace transform is f of s, what is the Laplace transform of df of t by dt? This is equal to s into f of s. Okay, so you can call this as what? C1 into the derivative of d by dt of r of t. Right? Right? Is it clear? D by dt of r of t plus the next term C2 into, what about the next term? Say if you have d square f of t by dt square, okay, this will be s square into f of s, and you know that there is a minus of f of 0, neglecting all those things, neglecting all the initial conditions. If you're taking only the first term, then it will be s square into f of s. So what about d cube f of t by dt square? That will be s cube into f of s. So from this you can evaluate the inverse. So this will be C2 into d by dt of d square by dt square of r of t plus C3 into the third derivative of the input r of t by dt cube. Okay, so this is it. Now what is this equation? This equation is what is called as the error equation, right? This is the error, and where C0, C1, C2, C3, all these are coefficients, and these C0, C1, C2, C3 are called as the dynamic error coefficient. Okay, these are called as the dynamic error coefficient, and by the knowledge of dynamic error coefficient, you can evaluate the error at any instant of time, and that's the drawback of the static error coefficient. In a static error coefficient, you can simply say whether the steady state error is 0 or infinity or a finite value. But in this case, you can find this error at any time by the knowledge of this dynamic error coefficient. Okay, so hope you understood this. The relationship, the difference between dynamic error coefficient and static error coefficient. Okay. Okay. Now let's study a relationship between static and dynamic error coefficient. Now, for a static error coefficient for a type 0 system, we know that the error coefficient is, we have already derived this from this C0, okay, C0 plus C1s into C2s square into, okay, etc. up to r of this into r of s. Okay, now for a unit step, we know that this r of s is equal to 1 by s. Okay, for a unit step. Now you are considering a type 0 system subjected to a unit step input. Okay, now you have r of s to be equal to 1 by s. Substituting in this, you will get this E of s to be equal to z0, yeah, z0 plus c1s into plus c2s square, etc. up to 1 by s. Now, we have already derived the steady state error ESS as limit s tends to 0 s into E of s, right? Okay. Now, when you substitute this, you will get this as limit s tends to 0 into s into, what is this E of s? Substituting this, c0 plus c1 s plus c2 s square, etc. up to 1 by s. This s and s get cancelled. Now when you apply s tends to 0, all these terms becomes equal to 0 and leaving c0, right? Leaving c0. Now from the steady state, from the static error coefficient, we have also seen this ESS to be what? ESS for a unit step input. Okay, now we have just seen that for a type 0 system. For a type 0 system, look at this. For a type 0 system with a unit step input, ESS is found out to be 1 by 1 plus Kp. So ESS is equal to 1 by 1 plus Kp, or Kp is the positional error coefficient. So from this, what you can say, these are equal. So C0 is equal to 1 by 1 plus Kp. What is C0? C0 is a dynamic error coefficient, and the dynamic error coefficient is related to static positional error coefficient in this way. C0 is 1 by 1 plus Kp.